Well, hi there. This is Chris Fregly from Amazon Web Services. I'm a developer advocate in AI and machine learning, and today we'll be talking about how to compare models in live production with multi-armed bandits. And of course, we'll be using reinforcement learning to train the multi-armed bandits. So let's take a look at the agenda. First of all, I'll talk briefly about the differences between A/B tests and then multi-armed bandit tests. How traditional A/B tests are static, whereas multi-armed bandit tests are a bit more dynamic, where we can actually add new variants to our test. So we'll talk about that in the next few slides. We will then use two pre-trained BERT models that we have trained with the Amazon Customer Reviews dataset, which is 150 million reviews from 1995 till 2015 from Amazon.com. We'll use two variants, one TensorFlow, one PyTorch. We are training them on the exact same data with the same hyperparameters, and we're going to push them into production behind a simulated application and figure out which model is going to outperform the other. Now, there really shouldn't be much difference because it's the same training data, and these frameworks, while they are implemented differently, they still pretty much have the same characteristics. They still use BERT, beneath the covers, the transformers architecture, and specifically Hugging Face, if you're familiar with that particular implementation of BERT. So we will then train a third model, which is our multi-armed bandit model. And for that, we'll be using something called Wabbits, which is a reinforcement learning framework. And we'll then deploy this onto Amazon, onto AWS, and we will then compare the two BERT models live and see how they perform. All right, so here's a traditional A/B test. Now, some of us might be familiar. If you're not familiar, you are probably in some A/B test right now. If you're using Netflix, if you're using Spotify, if you're using even Twitter or Stitch Fix. Yes, everybody uses A/B tests. And really what we're trying to do here in this specific case is we have trained a new model, and PyTorch will be model 2, and TensorFlow is going to be model 1. And so the TensorFlow model is out there taking predictions. It's predicting star rating from people's Amazon reviews, the actual product reviews. This is totally fictitious, by the way. This is not actually what's happening. I'm using a data set that is from 1995 till 2015. We are just simulating what you can do with these multi-armed bandits. And so with traditional A/B tests, we would split the traffic, and send 50% of our traffic to the current model and then 50% to the new challenger model. So model 1, which is TensorFlow, would be the champion model. That's the one out there today. We are trying out the PyTorch. Now, if for some reason PyTorch model 2 was not a good model, and all of a sudden all of our accuracy drops, we could potentially be classifying reviews differently. We may think bad products are actually good products. So there is real business impact here. So we want to sort of slowly shift the traffic. Now here I did something extreme where I just split 50-50. Typically you would do maybe 10% to the new model and keep 90% to the old, or send only certain customer or certain regions to this new model. There's different ways to actually figure out the split. But for this purpose, let's just say 50% of all traffic coming in goes to one or the other. Now, the problem is, like I said, there could be business impact here. And so there's really no way to reward a model that's doing better and then dynamically shift traffic. All this traffic is split, and this test has to run for the given amount of time that you have chosen. So if it's 2 weeks, if it's 4 weeks, and if you stop that test early because model 2, for example, was so bad, you now destroy the statistical power of this A/B test. So how do we solve this? We can use something called multi-arm bandits. Now, if you notice, I have a little slot machine shown in this picture here. Bandit is, of course, something that takes money from you. And bandit is a slang term for these like slot machines. And so if I have two different slot machines, I have two different arms to my, and so think of it like going into Vegas and sitting down next to two slot machines. And I'm putting coins into both. That's my traffic. I'm now pulling, and then one of them is going to pay out, or one of them is not going to pay out, or they're both not going to pay out. But what I want to do is if 2, for example, which would be the like PyTorch BERT model, really starts to become super accurate, then I might want to send more traffic to that and not have to wait for the duration of my test to complete, of my traditional A/B test to complete. At the same time, I still want to explore the original Model 1, because maybe that like particular slot machine or that PyTorch model was doing really well on a certain set of data that was early in the day for like whatever reason, but like really Model 1 sort of overall is the actual better model. So we don't want to completely abandon 1, but we want to shift more and more traffic to 2. If 2 doesn't perform well, we may want to shift traffic back to 1. So that's what I'll be showing you with the demo here in a bit. And so what I've been describing is explore versus exploit. So Model 2, for example, might be doing really well. We're going to exploit that like better model for a small amount of time, but continue to explore Model 1. We can finish this experiment early if we want to. If Model 2, after 1 or 2 days is the clear winner, then let's tear this down and shift all the traffic over to Model 2. I discourage that. I would still suggest that you run this test longer, at least cover 24-hour period, or if you have traffic patterns that are different throughout the week, I would run it for at least 1 week just to capture all of the different types of traffic. It's nice to know, though, that I can actually add a new variant. So let's say I was doing this test for 1 week, and maybe Friday afternoon I had this great idea that I want to actually try this third variant. Well, I can actually add a third variant. This Bandit will start to explore the Model 1, which is TensorFlow, Model 2, which is PyTorch, and maybe MXNet Model 3. Okay, and so this is all designed to minimize the regrets, which is really the business impact, and to maximize the reward and send more traffic to that winning model. So quick note about BERT. There's what I call BERT mania, tons of BERT variants. So BERT is a natural language processing, natural language understanding model. BERT has been pre-trained on millions and millions of documents and has a pretty good handle on human language, which is really cool. There's different variants of BERT depending on the language or the actual domain. So there's something called Camembert, which is the French variant of BERT. There's something called Patent BERT, which has been trained on patents. There's BioBERT, SciBERT, there's German BERT for German, there's BERTche for Dutch, and then there's clinical BERT. There's literally hundreds and even thousands of these BERT variants. What we are doing, so yes, I mentioned BERT was pre-trained on Wikipedia, on Google Books corpus, all kinds of digital text. But we now want to fine-tune this pre-trained BERT model and reuse or transfer this knowledge that BERT has learned on these millions of documents. But we now want to fine-tune with our customer reviews, our 150 million customer reviews. And we are going to train and pass in raw reviews, and then also pass in the star rating. And we are using star rating that was selected by the actual end user, by the customer, as the ground truth that we will use to then fine-tune BERT. So once this is done, and yes, I've done this offline with both TensorFlow and PyTorch. Once that's done, we can now use our variants to then make predictions and put them behind this multi-arm bandit. Let's talk a little bit about, so I just spoke about 2 BERT models. The third model that we will be deploying here in a bit is our Bandit model. And this model we will train with reinforcement learning. Each time a model is used, either model variant 1 or 2 for this specific case, so TensorFlow, PyTorch, as those models make accurate predictions, they will be rewarded. And the Bandit then learns which of these variants is actually providing the best accuracy. Now we're simulating and we're making some assumptions that when the user types in a customer review in our simple application, that they are actually providing the ground truth to then define that reward. In the real world, these rewards could be business metrics like increased revenue, like some more units sold, more like click-throughs. There's many different ways to define a reward specific to your domain. For us, this will be actually making accurate predictions, and we are using the user-supplied star rating as our ground truth. Now, there's quite a lot of different reinforcement learning strategies that specifically Vopal-Wabbit does implement. So there's things like epsilon greedy, Thompson sampling, online cover, bagging. These are all different degrees of the explore versus exploit strategy, and sort of how aggressive will we chase down the exploitation, or do we want to balance it with continuous exploration? And specifically, online cover is what we'll be using today. It's a pretty sophisticated algorithm that will actually create sub-policies or sub-models to determine and each sort of train separately and then come together in an ensemble to then say which variant should be chosen based on the specific context. And by context, I mean by the review that's coming in, maybe by the product category that this review is for. And I do want to point out that we are doing reinforcement learning on SageMaker. So SageMaker supports reinforcement learning natively, supports Ray, Coach, Vopal-Wabbit, Unity, and these are all inside of these SageMaker reinforcement learning containers that have been optimized for SageMaker, all based on the open source. Okay, so our demo, which I'm going to show here in a sec, so this is the entire production ready architecture here. So starting on the left is our application, which has a small little window to type in a product review. The user then selects the star rating, and so that's the assumption that we're making. That star rating is the ground truth. They type it in, they click submit. The application, step 1, asks the multi-arm bandit, which model variant should I use to make this prediction? And, so once again, this is a little bit of a fabricated, we are taking that text, we are then going to predict it, we are then going to compare it to what the user selected, and if it matches, we consider that a positive reward, a success for that specific model variant. So step 1 is to ask the multi-arm bandit, based on what the bandit has learned so far to date, which variant should I use to make the prediction? The multi-arm bandit says, okay, for the first one, use model 2, right? Because at first, the bandit doesn't know anything, and will just start sort of randomly exploring until there's an early winner. Then it starts to exploit, but it's still exploring. So step 3, the application oh yeah, I should step back. Step 2, the Bandit is tracking all of this data coming in. So what was the review? Which model ID did the Bandit actually serve up? And so that data goes into S3. And for that, we're actually using Kinesis Data Firehose, very, very lightweight way to get data out of your application or out of a multi-arm Bandit or some piece of code, either a Lambda, something, and then getting it into S3. Without having to manage a lot of Kinesis shards and all that, Firehose does it for us, has native integration with S3. So all of that data ends up as a JSON blob in these like different S3 buckets. Okay, step 3, the application actually makes the prediction on the variant that was served up, either TensorFlow Model 1 or PyTorch Model 2. The application then compares, and yes, I'll show this code here in a bit, and then sends through step 4, either A or B. If it does not match, it's a reward of 0. If the model predicted the same as what we are assuming to be the ground truth, which is the user selected star rating, then we pass a positive reward. And that reward information is then stored inside of S3 as well too with Kinesis Data Firehose. I'll show you the CloudFormation template, all the code needed to actually get this going in your environment. And then that data is then joined, and SageMaker runs offline and is continuously training. So every 500 predictions, every 5,000 predictions, every day, it will take all the latest code, all the latest the reward information, and then use that to train and push out a new multi-arm Bandit model. Super cool. So this is continuously happening. The data is being collected real time. The model is being trained in sort of mini batch mode offline, and then updating the multi-arm Bandit. So let's take a look at the code. Here's the demo. All right, there's some of the boilerplate, and then we're doing imports for the reinforcement learning. These are just basically like utilities. So we will do all of this from the notebook, by the way. Yeah, in fact, this notebook actually creates the CloudFormation resources, right? So using CloudFormation, this whole system is backed by 2 or 3 DynamoDB tables, 2 S3 buckets, and a SageMaker training job. And so here's the actual config.yaml that we use for this system. It's the name of the CloudFormation stack. Don't worry too much about that. There's our 3 Dynamo tables. There's an experiment table, model table, and so this is tracking the status of this continuous Bandit training. We can also specify the instance types to use. Here's the actual Vopal Wabbit SageMaker deep learning container. So reinforcement learning container that you could specify. You could also bring your own container as well if you have your own. Here's where we specify cover policy, the number of sub policies. Like I said, there's a quorum, there's a consensus that has to be made. That's why we have to choose odd numbers. And so num policies means how many policies will the cover algorithm or the cover exploration policy use to decide if it should be model 1 or model 2. Number of arms is the number of variants, so model 1, model 2. If I wanted to add a 3rd variant, I would change that to be 3, and then the multi-arm Bandit starts to send traffic to the 3rd variant. Okay, from there we slurp in the config YAML. Oh, and then also this is actually running within local mode just to speed up development and to kind of speed this up. You would certainly set that to false when it's time to run this in true production. It's still using Kinesis Firehose. It's still using S3 and still training the model. It's just doing it within this notebook versus the SageMaker. Okay. So, and yeah, this is all running within SageMaker Studio, by the way. So this is still using SageMaker. It's just a little bit lighter. Think of this like an ad hoc mode. That's the experiment manager right there. This is our client application that's simulating what I showed you on the left in that previous image. This is the application that's passing in. These are well-known reviews from the Amazon Reviews data set, and they have well-known star ratings. This is where we're actually calling the prediction. So TensorFlow, if the Bandit says to use action 1, yes, action would be a reinforcement learning term. That's what is the next action that the calling application should use. If it's 1, it's going to call TensorFlow. If it's 2, it's going to call the second, the PyTorch model. Here we actually calculate the difference. This is where we're going to figure out the reward. So we know the star rating because in our simulation, we have that data that's simulating what the user would have clicked when they submitted the review. If there's no difference, meaning that the BERT model predicted the same as the known label, then it's a reward of 1. Otherwise, it's going to be reward 0. So this all matches kind of the left portion of that diagram I showed earlier. Here's where we're actually going to invoke the simulator. We tell it BERT model 1 is TensorFlow, BERT model 2. Those are the 2 arms. Now we're going to train a model. We are actually training this model without much data, but the model will get better as it sees more data, makes more predictions, and then compares to the ground truth. So here's the actual train Voepel Wabbit. There's the hyperparameters, as I mentioned, the cover policy, the number of sub-policies, number of arms. Here's some metrics. Now, yeah, so keep in mind too that there is not much data here when we first deploy the Bandit model. You can certainly pre-train the Bandit model on historical data, so you don't always have to start fresh. This is a sample where we started fresh here. Now we're gonna actually do this, so forgive the scrolling here. We're actually going to run 5 loops and make 100 predictions per loop. And this basically is our training data for the Bandit. The Bandit then gets the reward, compares the reward, and then passes that reward on through Firehose, through all the different parts of this production system. It can then do the evaluation, so it's going to continuously train a model. It's going to compare the evaluation metrics. So just like any model training, we always want to evaluate the model, and we can then compare to the previous model that was out there. Maybe this new data led to a super bad model. Here we're actually comparing what was the score, and in this case, lower score is better, just the way that these metrics were defined. So we have the score for the previous model. Think of this like loss, right? There's accuracy, which you want to maximize, loss that you want to minimize. Okay, and then here's some of the results here. So I'll show some of these charts in a sec, but we are tracking number of the actual invocations. So how much traffic did the Bandit send to variant 1 versus variant 2? So it looks like variant 1, which is TensorFlow, actually got a little bit more traffic. Now, keep in mind, this is only 500 data points. Probably wanted to run the experiments a bit longer, but for time's sake, we capped it at 500. There's really no reason why TensorFlow should be better. Like I said, it was trained on the same data. It was trained with the same hyperparameters. And so here's a chart showing the actual invocations. So those same numbers I had shown before. This just gives us a little bit of time. So this is over time. It looks like PyTorch was initially getting all the traffic, and then it was balancing it with TensorFlow. But they both ended up about the same, as I think they should. This is the actual action probability. So there's two different types of probabilities that we will be analyzing. So there's an action probability. So it's saying for variant 1 or for variant 2. So 1 is blue, that's TensorFlow. 2 is the lighter orange. Yeah, so so 1 is like the action probability, and then on top of that is the sample probability, which we'll look at here in a sec. So mean action probability for BERT model 1. This is which model is the Bandit, which model does it actually think will be the better model? So 0.74 versus 0.69. Now on top of that, there's a sample probability. And so this is really where the exploitation piece starts to happen. And that is controlled through these hyperparameters, through the sub policies, through online cover, and the sample probability samples and says, okay, maybe action probability was in favor of the TensorFlow model, but I still want to explore too. And so here we could see in orange is PyTorch. We see initially was the one that was chosen. Yeah, so all of this, so these charts all match, right? They show that, like initially PyTorch was getting most of the traffic, and then slowly the Bandit started to work in TensorFlow. So now the mean sample probability is 0.499, so yeah, almost 0.5, and then 0.476. So still more was being sent to BERT model 1, which is what we saw in the charts. Now let's take a look at what's called the mean reward. And this is 100 rolling mean reward. Means, so this is 500 predictions. You can't really see the bottom there due to the screen size, but so this is 500 predictions. And we're showing here that the Bandit started to increase. So what we want is this to go as high as possible. And so, as the Bandit started to explore, it started to find, maybe the TensorFlow model doing better. It was exploiting. And then it started to explore. So, started to kind of dip down there. Then it didn't want to go too far down. So then it sort of corrected itself and started to exploit, and then explore a little bit, and then exploit. Okay. And so ideally, so there's the number of predictions. I believe this chart actually calls that x-axis the number of the instances, and that's because this is what we're using to train the model. So while we are actually analyzing this for reward versus regret, because keep in mind, if this chart went all the way to 0, we would be, this has business impact. That means we have not maximized reward. It means we have maximized the regrets, which is not good. So, this shows a nice healthy balance of trying to explore and exploit. Okay, let me pause this and go back to the slide here. Okay, so quick summary of what we saw. We actually compared two of these BERT models, one TensorFlow, one PyTorch. We trained a multi-arm Bandit, and this is what we saw. So over about 5 minutes, we see more traffic starting to be sent to the TensorFlow model. Now really, I wouldn't make too many false conclusions on this. This is a very short amount of time. It was a very small amount of data. This certainly does not mean TensorFlow is better than PyTorch by any means. And in fact, it shows that they are about equal. And keep in mind that we're not tracking performance or anything here. This is purely just based on accuracy. So summary, use multi-arm bandits if you want to do more dynamic tests, if you want to have this concept of a reward that can dynamically shift traffic between the variants, if you want to add a variant. use multi-arm bandits. Multi-arm bandits also support many different explore exploit strategies, and they each have different hyperparameters. Some of them work better for certain situations. And also, just a quick reminder, SageMaker does support reinforcement learning natively. There are many built-in reinforcement learning like models you can try. And thank you so much for your time. Quick reminder, there's a new book coming out by the O'Reilly folks. Me and my co-author Antje Barth, we dive much deeper into the Bandit stuff. Yeah, so check it out. This should be available early 2021. We have 12 chapters, 500 pages, hundreds of examples, and we cover quite a lot of ground. We've been working on it for 1 year, and we're super excited to get it out into people's hands. So yeah, check it out. Here's a couple more resources. GitHub repo that actually has all this code is that second link. There's an AWS blog post on multi-arm bandits that goes into some pretty good detail. There's also Vopal Wabbit has lots of really cool documentation, very, very useful documentation that's been curated and is very mature. And then also check out some more of the SageMaker reinforcement learning containers. Thank you so much for your time, and hope to see you soon.